Hey everyone, this is Divi over here. Today we'll be learning about some queues. I'm just reading part of this book if you want to download it. It's a 2009 third edition of Introduction to Algorithms. Skip to the middle part, so let's dive in right into queues. So we call the insert operation on a queue NQ. We call the delete operation DQ, like the stack operation pub. DQ takes no elements. So when you think about a queue, think about these people. Just moves the pointer to the second element. Usually we do, but instead we just move the head and the tail. Place for tail, and we'll DQ just newly arriving customer. So imagine the tail is a pointer right here, or over here originally. When a new person comes in, the pointer moves over here, if that makes sense. It shows queue with most n-1 elements using this array with queue head. So I guess this is the full point, yes, right here. So this is an example. For example, the tail is on an empty spot and the head is on the first elements. Then doing these sort of operations, they do NQ, which is adding an element, NQ, which is adding another element, and NQ again, which is adding another element. So you can see first it moves here, so adds element 17, then 3, then 5. The tail is moved over here for the next element. What's interesting is this is a circular queue, making it so that even though it's one single 1D array, even when it reached the index 12, it went down to 2, showing how really the only two things that this data structure is dependent on is the tail and the head. That defines the whole data structure, which is pretty interesting. Then later in the third one, it DQs, so again it moves that one same way how we're moving the pointer, just like this. The elements in a queue reside in locations, head, where we'll wrap around in the sense the locations Q1 immediately follows location Qn in a circular order. When Q.head equals Q.tail, that Q is empty. Initially found that Q head equal to 1 if we didn't underflows. Okay, so if you try to Q or if you try to DQ something from a MDQ, it just underflows, so don't do that. So when Q.head equals this, it's full. Interesting. So like the circular thing we're looking at over here, if it's all full, then it won't work. Process NQ and DQ if omitted, error checking from underflow, overflow. Okay, so we have removed it, but this is basically the code. It's saying that we take in the element of Q, we take the Q.tail index, and that is the value X that we get. And if the Q.tail is equal to the Q.length, if the index is equal to the length of the whole thing, then Q.tail equals 1, else Q.tail, the index equals the tail plus 1. Basically saying if it's max, then we just move the tail to the first one. Else then you add one. DQ does a similar operation for the other thing. Here are some exercises we can go through later. But that was Q. I learned about stack a little earlier, so let's go through that. Let me find it. So, just going over the broad overview of data structures. It's based on arrays and pointers. I think that's a really straightforward way to think about it. Any array that you have with n number of elements, n1, n2, all that's defined with is the different pointers and the array itself. This makes it so the data structures that we create are very efficient. So stack is the last in, first out. Specifically think about it as a stack of plates. When you stack plates on top of each other, you always take the first plate on top, and then take the first plate on top. And then when you're adding more plates, you add it on top. Likewise, you can do it in a stack a similar way by inserting via push and then removing via pop. Again, it takes no arguments for the remove simply because you always add last. So depending on the operation type, insert, if you're adding at the end, is always going to be O1 time complexities. Removing will always be O1 time complexity. But if you're adding it to somewhere in the front or in the middle of the list, you'll have to shift all the elements, which might make it an O n time complexity. So if you're adding other elements, maybe linked lists would be a better alternative, which we'll go over later. So if this is empty, actually I'll talk about this graph. This is just an image of a stack graph. You can see s top is equal to 4, just showing how the top pointer is over here. You're adding some, then you're removing some. Remember, s top is equal to the index at that point. It might seem confusing because you're thinking top might be the index, but no. S top is asking what index is the max, and so it's giving us the index of 6 over here. So array implementation of stack. Stack elements appear only in lightly shaded things. Everything else is, again, not removed, but is just moved across. Because if you think about it with data structures removing, if we were over here, if we were removing this from the list, we'd have to cancel this out and shift everything for a queue, but simply just keeping it there and moving the head is the easiest way to go on time complexity wise. So again, queue is a first in, first out. Just like a queue at any restaurant, if you're ordering, first person always gets to go and order first, the last person order last, depending, and then everyone has to join the queue at the end. So we already looked at this instance, but in essence, queues wrap around when unable to go further left, uses 2 pointers, head and tail. Now let's move on to linked lists. You guys can try out these problems and figure it out. I'll go over these exercises in another video, but for now, let's keep on learning. So what are linked lists? Linked lists are data structure in which objects are arranged in a linear order. Unlike array, however, linear order is defined by the array indices. The order in a linked list is determined by a pointer in each object. Again, the same pointer. Talking about how all data structures are kind of made by these pointers. And linked lists provide a simple, flexible representation for dynamic sets, supporting through not necessarily efficient all operations. I'm wondering why my camera's not showing up. Let's try to fix that. Okay, I think you can see my camera now. Okay, I don't know why you aren't unable to see my camera, but it is what it is. Let's keep on going. Shown in figure 10.3, each element of a doubly linked list is an object with attribute key, 2 other port attributes, next and previous. Okay, this might seem like a bunch of words. Let's first look at all the operations on page 230 and how a linked list looks like. Okay, well, most linked lists that we're going to be using are going to be doubly linked lists. Usually you won't use singly linked lists because singly linked lists look like this, which means you can go from one to other, but you can't go backwards, which is a little unfortunate. Okay, linked lists are shown as follows. It contains the key, the previous index, and the next index. And this is specifically nothing but storage key of where it's stored in the hard drive. It's like all data and bits are stored in specific locations on computers. And you can find the locations on the computers using Java or another language. And I forgot the complete command, but like when you say print array, for that reason, you don't or system.out.println array in Java, you don't get the actual array, right? That's why you have to do some other print command, which I forgot on the top of my head, but it instead gives you some sort of string. That string is the location. Likewise, all objects in Java and every other language has a location for each of the next index. So in this case, we've labeled this as the head, and we're saying there's no previous node shown on the left. Instead, the next node is on the right. The previous key is going to point back here. This is going to point over here. And seeing this key, we can see the next one is this. So what does this mean? This means if we call this A, if we call this A, we call this B, we call this C, we call this D, we'd say, oh, next key is B, oh, the previous key is A, the next key is C, oh, the next thing is, you get it right, B, D, then this is C. It makes it really easy to traverse from one thing to another. However, when you're indexing through a regular array with n digits, or n size, 1, 2, 3, let's have a 3 size, it is an O of 1 operation to index, because all you need is the index. You'd be like, oh, what's the second one? Boom, right here. Or what's the first index? Right there, right? Very easy. However, with linked lists, it is a O of n time complexity, but instead of adding an element here would be very difficult. It'd be very difficult to add an element to a regular array. Linked list, on the other hand, if we wanted to add an element 6 with all we need to do is remove these two right here, add the arrows going into here and back, change it to point towards C1, change this to point towards D, and change each of these to be C1, C1, and all like that. O of 1 operation, O of 1 operation to add. So however, O of n is the worst case scenario for finding certain things, but O of 1 is the time complexity of actually adding a specific thing. So it's very simple, and honestly, this is probably one of the most useful data structures when trying to add. Let's keep on reading, now you understand that a little bit. So we have the two next and previous we talked about. Object may contain other satellite data, okay? Element X in the list, x.next points to the next one, no predecessor, then therefore the first or head of the list, okay? We saw that X, it's not, okay? That's when it's the previous equals this, then it doesn't have anything. Similarly, if it's equal to nil, has no successor, and this is the last, the same way. If dot next equals this, right? We get that. If L dot head nil is empty, the head points to the first element. That makes sense? Hope it does. Okay. Lists have several forms: singly list, doubly linked, and may be sorted or not sorted, circular or not. If the list is singly linked, we omit previous, right? I'm saying it just, if it's singless, you just go one to the other, to the other, to the other. But most data structures you'll be going through will be doubly linked. If a list is stored in linear order, corresponds to the linear order of keys. The maximum element is the head, maximum element is tail. Minimum, sorry, but yeah, you get that. If the list is unsorted, then it can be in any order. Circular list, previous points to the first, yeah. I think you can understand if it was a circular thing. At one point, this will be pointing here, this. And then it'll be pointing back. And then even if it's doubly linked, you'll see how it's like that. I'm not going to draw all the arrows, but you get the point. Okay. What was the last sentence? We can think of a certain ring of elements in this remainder. We'll see the links, which we are working are unsorted and doubly linked. So this is actually the most common sorted and doubly linked, just because it's a little complex to make a sorted, doubly linked list, or just linked list, or just any sorted linked data structure. So we'll just assume it's unsorted for most of this. So the procedure of searching is the list search LK with key K. We talked about this earlier. So you're searching for this element. I want the element of key K. Only way you can do this is by starting at the first element, going to the next element, going to the element, and on. For example, if I needed element 3, I'd have to go to the first element, which only has the next and previous information. So let's say it's like a scavenger hunt. Oh, I know what the next one is going to be. Boom. Oh, shoot, this is index 2. Now I know what the next one is going to be. Oh, this is index 3. But we can't skip to index 4 from index 3 just because we don't have the information. We don't have the information of how we're going to get there. Call list search returns a pointer for the third element. Likewise, this should have been for, I'm sorry guys, what? Oh, that makes sense. So it's looking for the key, not specifically the index. This refers to the actual key. I wouldn't say value, but it's kind of like, yeah, the key is looking for. So above it's saying 4 is the third element, if that makes sense. Apologies for that confusion. List search. Again, we were talking about how it takes all n time. Worst case, since it might have to search through the list in this fashion. Inserting is O of 1 complexity, just because that's how the head points to. You can look at the code right here if you want. So next equals head. If this equals nil, does not equal nil, then you do this, else you do this. Okay, pretty simple. Deleting similarly is also, I didn't talk about that, but it's simple. It's as simple as adding it. All you need to do is just boop, do that, and then change the 2 indexes. You change this to D, change that to C, right? And you get back to the normal one. So it's O of at 1 time complexity. Sentinel nodes. Oof. For list delete would be simpler if you could ignore the boundary condition. Sentinel is a dummy node that allows us to simplify boundary conditions. For example, suppose we provide L with an object L.nil. Oh, this is literally... Sentinel nodes are really important, so for now, I'm going to make this into another video. But you guys can read this if you want. I'll just give you a real quick page view. Again, this is MIT's book, so you can thank them. And it's really helpful, so yeah. I'm going to end this video right now, but hope you guys join us for the next one. See you.